Okay, everyone, we are going to start the session. Today is my honor to introduce Dr. Sang-Hyun Lee. Dr. Lee is a Robert B. Harris Collegiate Professor and John L. Tishman Faculty Scholar in Civil and Environmental Engineering, University of Michigan. He directs the Dynamic Project Management Lab at the University of Michigan. He is the founder of Kinetica Labs, a pioneer in sensorless motion capture for ergonomic risk assessment, which was acquired by Velocity EHS, where he now serves as a machine learning scientist. He is an elected member of the National Academy of Construction and ASCE Fellow. His research advances empathetic construction and infrastructure management by leveraging wearable robotics and automation to enhance human performance. He has received numerous honors, including the ASCE Daniel Halpin Award, ASCE Thomas Fitch Rowland Prize, FIATEC Outstanding Early Career Researcher Award, CII Distinguished Professor Award, and University of Michigan Henry Russell Award, among others. He has published over 280 peer-reviewed publications and has a H index of 67 and holds 7 US patents. The title of the presentation today is Advancing Construction Safety Through AI and Computer Vision, Ergonomic Assessment and Real-Time Monitoring. So I'm going to give the ground to Professor Lee. This is an honor to host you. I remember since when I was a student, you were aspiration for many of us young researchers who was coming to the construction community, and we has always followed your research, read your papers, and learned from your lab. Professor Lee, please, session is yours.
Thank you so much, Professor Asmali, and also thanks for very nice the introduction. Also thanks for all the attendees, and I hope my talk is not going to be too boring, but hopefully we can have the exciting discussion about the new eras of the artificial intelligence, how that affect our ergonomics. So my title will be AI-assisted ergonomics, and particularly I'm going to talk about the application for preventing musculoskeletal disorders and the fall risk. So this is today's outline. I'm going to briefly talk about what we mean by AI-assisted risk assessment and potentially interventions. Then I'm going to talk with the two applications, MSD risk. Particularly, I'm going to talk about here is with the cameras, meaning that I'm going to talk about the application of the computer vision. And then I'm going to move to the second one, that is a fall risk detection. And in this case, I'm going to use talk about the application of the wearable biosensors. And as many of you already have like a smartwatch and the fitness tracker. And then I'll draw a brief conclusion, and then the acknowledgement and reference will follow. So first, let me talk about AI-assisted risk assessment and intervention. So traditional risk assessment, and I'm going to talk about one of the risks, which is MSD, musculoskeletal disorder risk. And particularly when I worked on this area, I had a chance to interview more than 100 professionals in the industrial ergonomics. And then when we think about traditional risk assessment is like a manual assessment, and what is the issues or the problems from the manual assessment? And something that we identified as the problem from the manual assessment is time consuming. Just literally, it takes a lot of time. And another thing that we noticed is it has limited coverage, meaning that you would like to evaluate all the possible risk in your job site. But because of its time consuming, equals effort driven, basically you cannot have wide coverage over your job site. So typically, in case of MSD risk, 10 years ago, 15 years ago, it has been known that only 10%, and maximum 15% of the job site can be covered, right? So there are a lot of the areas and the places that we are missing for this job risk assessment. And of course, this is a manual assessment, so it is error prone, but I would like to frame as a more inconsistency. because everybody has a different view to evaluate, for example, checklist based for the risk assessment. So it comes with inconsistency. And then also if you would like to have a manual assessment, and as a professional, you may not be able to order the manual assessment, particularly for data collection, then you need to train your assistant or even interns, but it requires a lot of training. So what AI can do for this one is, of course, the AI can deal with this time consuming. It has wide coverage, and it is consistency. I'm not going to say that it is zero error-free, but it is more like a consistent. And also, it doesn't need, if once we train the model, then we don't need any consequent training, so there is no need for the training down the road. So this risk assessment is what AI has been emerged, and then we see that it becomes very popular nowadays in the job site. And one of the main drivers for this AI-assisted assessment is because we have continuous data. We can have cameras and we can have wearable sensors. So it means that now we are able to have continuous data from the job site. That actually is one of the major drivers to adoption of the AI, because AI, and if you want to do the job site analysis, basically we need the data. Then nowadays, also I see that AI has been a great potential for now even intervention recommendations. So we can do risk assessment and we can get assistance from AI about the risk assessment. And then also we can see that we can have AI's potential recommendation. So we as a professional can only focus on what if analysis or what if the basically decision-making process. So that is the general story about the AI-assisted risk assessment intervention. And that's what I found that it is great potential to reduce all the risks in the job place. And that's what I have been studying and translating to the practice. So having said that, so let's talk about my first application, musculoskeletal risk, and with the camera. And particularly, I'm going to talk about with the smartphone, because basically most of us now have a smartphone. So I'm not going to talk a lot about the significance of musculoskeletal disorders in the United States, but we all know that, for example, 30% of the incident and the injuries in construction, particularly days away from work, is because of the musculoskeletal disorders, work-related MSD. And then in terms of the workers' compensation from MSD risk is more than $34 billion per year. So it is very important issue in the job site places. Then if we see the risk assessment and MSD risk evaluation, basically what we are trying to do is we try to understand their postures, particularly joint angles. Joint angles, for example, to what extent I bend my back means basically severity of the posture. So we focus on joint angle, basically postures, and then it goes to the typical observation method like a lever, ruler, OWASP, or now sleep indication, Snook table. And so that is what we have been using for MSD risk evaluation. So 2016, I saw great potential, and also I have approved that it is computer vision based, basically sensorless motion capture, only using, for example, smartphone, can have a great potential, particularly to automate joint angle calculation. That is the most bottleneck in the risk evaluation. So I found a company called Kinetica Labs, and we pioneered and we commercialized it. So basically, idea is using computer vision, pose estimation, we collect the body angles, basically severity of the posture, then we can automatically identify what is a repetition, how frequent do we observe depth, posture, and then duration, how long. Then it can be connected to the typical, the observation-based. This is an app that we developed almost 10 years ago. So you can see that now it is connected to the continuous body angle calculations for each body joint, and then it connects with the Riva ruler so that we can have risk assessment. So then that one, the 10 years ago, we introduced the 2D, but we are living in the 3D world, and then we definitely need the 3D human motion data for risk assessment. Right? There are particularly two reasons for we need a 3D for risk assessment. The first one is based on the different viewpoint, your body angle calculation estimation would be much different. The three angles that you see, depending on the viewpoint, it could be from 0 to 180 degrees. So we are advising our professionals try to maintain a very clear line of sight, at the same time very specific range of the view, but that doesn't mean that that is always allowed in the job site because of the constraint in the workplaces. So we need to deal with it, meaning that we need a 3D. And also another thing that we noticed that it's almost impossible for high degree of freedom joint, for example, wrist. If we calculate the joint angles of the wrist, it can have a flexion, extension, and the pronation. But if we have a 2D, it is just impossible, right? So we have high degree freedom joint, which is wrist, neck, and shoulder. So those are almost impossible with 2D. So we would wanted to develop the 3D posture estimation. And then if we want to do artificial intelligence, we need a 3D data set. So there are some data very widely available 3D data set for AI model training. And one of the most well-known data set would be human 3.6 million data set. But the problem of those existing data set only, particularly for ergonomic risk assessment, MSD risk assessment, is that it just has an insufficient 3D key point. And in case of human 3.6 million data set, it only has 17 effective joint, which is not sufficient to calculate all the body angles needed for MSD risk evaluation. So we use our Bicon and the IGB cameras, and then we propose the 66 key point to address those issues. So we need to select or write the 3D key point. And the first one is we need to have a sufficient 3D key point, right? So we need to calculate all the flexion, deviation, and pronunciation. So we need a sufficient 3D key point to calculate all the body angles. And also we need to have, another thing is we need to have a visibility. Most of us familiar with the plug-in gate key point, but if we just use a plug-in gate key point, it doesn't have a lot of the visibility. We are talking about camera-based, computer vision-based ergonomic risk assessment. And to do so, we need to have a visual features in the key point. So for example, instead of the two key points on the forehand, and we are using the key point in the left ear and right ear, so that the marker, the key point is basically has a visual features. Then we collected 3D data from 20 subjects with a diverse height, weight, and so that we have diverse BMI. And then we particularly focused on manual material handling and assembly tasks. So for example, here, poke, push and pull, and assembly overhead. And then to have a motion variability, we actually asked each subject to repeat same task as much as they can for 3 minutes. So even though we say assemble overhead like this one, it can have a more variation. So we can have a lot of the variation in the data set. As a result, our data set has more than 5,000 task variation and more than 1.8 million distinct frames and total 6.7 million frames as a data set. Once you have this 3D motion data set, now we are going to use our computing pipeline to have the 3D pose estimation. So the way that we do is first is a 2D pose estimation. And then once we have a 2D skeleton, then we have a 3D pose estimation from basically using the 2D and 3D lifting. Then we are able to have all the possible body joint, 22 angles in the 6th joint, which is ready for all the possible ergonomic, the MSD risk evaluation. So we tested these 22 3D angles, and then this is all the angle names. And then our mean absolute error, which is basically overall error, is a 6.2, including all the wrist angles. But wrist is very hard to evaluate the angles because it is just very little, right? It is very hard to differentiate the body angle. But if we exclude the wrist angles, it is 5.1 degree and overall. And also we measured median absolute error which means the typical error. If you apply the pose estimation, body angle calculation to the real world, typical error is also very important. So we also measured the median absolute error, which has 4.4 degree. So this is the demonstration of the body angle calculation that coming from the 3D pose estimation is in the real workplaces. You can see that all the 3D body angle are here, the 3D skeleton, and all the possible body angles that are shown in this one. So that has been translated into practice using by Velocity HS. Now it has been used more than 500 organizations, and then 600,000 assessment has been made, and which resulted in more than 200,000 interventions. So we are achieving the year over year 17% MSD reduction. Here, then one thing that I would like to highlight is that I talked about using manual evaluation. It is very hard to achieve the wide coverage of the risk assessment, but this vision-based, smartphone-based MSD risk evaluation really democratized the use of MSD risk evaluation so that you can see a significant number can be done with just a smartphone. Then what we have been working on is, it is great to have a posture repetition and duration, but also if you want to do, like, for example, biomechanical analysis, we need external forces. So we also have been working on only using smartphone to estimate the forces. The way that we do is we have 3D skeleton. This is a simplified 3D skeleton. And then we developed our own force estimation model, which composed of kinematic modeling model, basically changing to the rigid body, and then physics guide, inertial force risk construction, and then we have optimization. So the way that what it looks like is that if we have a 3D skeleton, and then we predict the external force. In this case, the red one is our estimation, and green and blue are basically ground truths. And blue is the Gaussian filter was applied because there is an inherent noise in the force estimation sensor. So we can see that it is very following the similar the trajectories of the ground truth external forces, which can open the door for the biomechanical analysis. That's what we also have been working on. So far, I have been more talking about risk assessment. Now let's see the potential of the AI for the intervention. This is an ongoing work, so I'm going to briefly introduce also what we have done for intervention recommendations, interventions using the AI. So again, if we have a smartphone, we have video, then we have a 3D port, and also we can use the external force estimation that I introduced, or you can just put away then basically we can use the 3D SSPP for biomechanical analysis, or just using the 3D pose, we can do a Liba-Lula ergonomic risk evaluation. If you look at the phone, actually phone has other features. For example, what we can do is it can have voice and text comments, so we can also identify each specific task. And then nowadays, also some of the phones comes with the LiDAR scan, so means that we can actually scan the surroundings. So what we can do is, okay, we have a pose here, and then we have a task description, and we have the side scan, and then if we put all together into the physics-based simulation platform, what we can do is we can actually simulate what is happening, like a worker's posture, into the virtual world, and which is physics-based. So we can actually identify the exact and what kind of posture the worker can take. In other words, if we can see that if the posture is, for example, bad, if posture is not safe, posture has a very low score, then we can try with the what-if analysis here to see that how we can be improved, and then we can put it in basically we can decide, okay, this is not too safe to perform, then what kind of the redesign of the job site or task can be done for the interventions. So let me show the quick demo. So basically what you can see here is we have the real work and then pose estimated, and then that is showing in our physics-based simulation. Right. Sorry for this. And then we can also see the score, the 3D SSPP or Nash lifting equation score. And then what we can do is we can import the side scan as well as the task description. So we can do the side scan of the real world, and then we can see that how workers can improve their postures. For example, here, the previous one, the real one, what worker has done is basically stoop. And then it is reaching their arms, hands to pick up the boxes. But if you can see here, actually a worker is trying to use the squat, and to one leg is actually step over to the step so that it can have much ergonomically safe postures. And then we can see that their impact on the 3D SSPP or Nash lifting equation. So meaning that the AI can generate, okay, I understand that this is a real situation, that what kind of postures can fit in this real environment? What could be improved? Or then if we see that there is no way to improve the ergonomic score, MSD risk evaluation, then what we can do is we can simply change job task description, and then we can try with the redesign of the workplaces, and then we can see what is going to be impact before actual implementation in the job site. So it is one way that shows that AI can actually help intervention recommendation, so we can decide what is going to be the best for our job places. And another thing that also we have done as to include the intervention recommendation is basically use of the generative AI. So for example, nowadays, the advancement of the generative AI, for example, ChatGPT and Gemini is unbelievable. And what they can do is that if we put the image and then they actually can explain, if we put the comment like explain this same image in a single sentence, it can actually explain what is happening, scene understanding in this image. So we would like to use see the potential of visual to text generation. So what we did is that, but if we just use the ChatGPT and Gemini at this time, we still see that it is not much accurately described in terms of the musculoskeletal disorder problem and solution. So we trained with Nash ergonomic guideline. And also at the same time, it has been known that the generative AI doesn't have a lot of the accuracy in the pose estimation. So they actually sometimes confuse it what kind of posture they are trying to describe. So we put the 3D pose, which we already achieved, and then put it there to see that the generative AI can recommend problems and solutions just looking at the image. So this is the demo that we have. If you see, we put the image here, and then it creates a 3D pose, and then it identifies what is a problem and the solution. So in this case, lifting heavy concrete block with a bent back can cause back pain, and then solution is use lightweight concrete block. So our accuracy, this one, Parlibi is our one, accuracy is almost 85%, which is greater than the typical generative AI out there. So meaning now we can also get the kind of intervention recommendation just using smartphone and to see that what could be done. So while we are moving onto the now video, because we would like to have a much more rich information, and also we can get the continuous data, the video. So far, I have been talking about the MSD disk with smartphone and computer vision. Now, let me talk about this another application. Now, I want to talk about the fall risk, at this time using the wearable sensor, for example, wristband. So falls are the most frequent and fatal source of injuries in construction, but also in our daily life, in our built environment, it is very serious issue. 10.9 million emergency visits in the US every year, and over $180 billion are spent in medical costs because of falls in the United States. So fall is very serious issue. And this hazard, slip, trip, and fall hazard is not only in construction, but also other places. It's everywhere. So what we try to do is first, using the wearable sensor, in this case, IMU, which measures the acceleration and which also has a gyroscope. And so IMU-based STF hazard exposure detection in construction. So what we did is that we put the IMU sensor into the waste using the vertically. And then construction workers just walk around the site. We basically identify abrupt movement, bending and jumping. And then we can use the threshold to identify abnormal patterns. So for example, specifically what we did is that we try to understand the gait features, extract the gait features. And then eventually what we would like to measure is a gait variability. If you have just regular working and normal working, your gait variability is not going to be high. But if you have hazard exposure, your gait variability is going to be increased. That's what we are trying to capture with this calculating gait variability with the Mahalanobis distance, and then train with the bidirectional LSTM, and then we see the difference between in case of exposure to the hazard or just train regular working. So we applied a couple of construction job sites working with the 16 construction workers with 6 trade. And then we are able to collect 60 hours of the data, and which composed of almost 10,000 training steps and 18,000 and testing steps. So what we try to measure is that our target STF hazard exposure, for example, in case of risky movement, jumping and carrying, and inattentive working, like using a phone and chatting, walking around the construction site, and then risky environment like slopes and obstacles. So our result, using the one that I introduced in the previous slide, the average accuracy is 94%, so it actually identify STP hazard nicely. So once we identify STF hazard in the construction site, we can actually map as a kind of the hazard map to show that which area particularly has this hazard. Also, it can be simulated over the time. As I introduced earlier, but the force is in the everywhere. So now we would like to have a more wider applicability, particularly to apply to our built environment. To do so, the IMU sensor in waste with the vertically may not be ideal solution for normal people and every use. So we would like to move the sensor location from waist to wrist and using basically a typical smartwatch. And also, we would like to address the variability of the force, meaning that all the different contexts exist in case of fall. So it is try to collect all the possible scenarios of the fall and train the AI model would be not feasible. So we would like to address the variability of falls. And another issue is that there is a transitional working, meaning that if we see the abnormal motion patterns from exposure to fall hazard, which could be very similar to the transitional working like the jumping, bending, and fall news. So we need to differentiate such transitional workings to accurately identify the fall hazard. So what we use is, the first one is we use the unsupervised graph-based approach, meaning that basically it is a training-free approach. So you don't need any AI training, and then we just start collecting people's the IMU data. We are going to identify the abnormality using the graph-based one. So another one, particularly for transitional working, what we did is that we used the EDA, electrodermal activity, which measures the electrical conductance, a change in the electrical conductance in the skin. So many smartwatches nowadays have an EDA, so we would like to use EMA and to differentiate transitional working. The way that it works is that the EDA basically measure people's arousal. And if you encounter into the fall hazard, which is stressful event, then we are hypothesized that there will be an increase of the arousal. While the transitional working, it is not the stressful one, it is your kind of intended the working. So it doesn't show a lot of high arousal, which what we would like to use EDA to differentiate that. And then combine them will be fall hazard index, which is from 0 to 1. So we tested in the real world environment, and we have 70 people from University of Michigan campus, and each one is wearing 2 weeks, and the age group is from 19 to 80 years old. And also the data collection span is more than 6 months because we would like to capture STF hazard from the different seasons as well. Also to collect the ground truth, meaning that there are 4 perceived fall risks, we also use the ecological momentarily assessment-based self-reporting app. EMA basically measures repeatedly samples people's real-time experience and the behavior. So we developed our own app for EMA measurement, and then we are able to collect more than 4,300 working tree, and then we found that 483 significant fall risk. So this is the one video that shows that people walking around the University of Michigan Central Campus. And this is some debris. And then this is the app that we developed. So once you have something for hazard, then you are going to put the information about it, and then you take the pictures. That's the way that we collect this all the data. Then we applied the unsupervised, and then also we used a graph-based as well as the IMU. And then our result is that unweighted average record is 87.25%, which is very promising. So we haven't used any training data set. But also we are using the wristband. We are not putting the sensors in a location where our gait is more apparently collective, like anchor and all waist. We put the wrist, and then we are able to get the 87.5, 25% of the recall. And also something I would like to share is that we mapped all the significant fall risk in our UN Central Campus. And we found the red dot here is a fixed, kind of fixed hazard, which is kind of permanent hazard. And the yellow dot is actually temporary, like debris. So we found that almost 35% of all the fall risk hazard are basically temporary hazard, which is most of them are debris, meaning that it has been emphasized that cleaning up the street and pedestrian street or any other our infrastructure maintenance, it has been much emphasized. But what this data tell us is that it can actually go long way. It actually can make a great impact, right? That is really important because almost one third of the fall risk are something that we can easily fix. And that is something for our infrastructure maintenance. This is something that we can do. And it just shows that the importance of this fall risk assessment. So let me conclude it. So basically, we see the emergence of AI and popularity of AI. And AI has been mainly used for risk assessment. And one major driver is a continuous data. We have sensors in everywhere. But also now we see that the capability of AI has been greatly improved. And so now we see that also actually AI can be used for intervention recommendation. So professionals can only focus on the decision-making process that is happening in the field and the practice. I would like to acknowledge my current and my former PhD student and postdoc who have been working on this area. Also, I would like to acknowledge my industry collaborators from Velocity HS and the Liberty Mutual. Also, I would like to thank my financial sponsors, NSF, Velocity HS, and Liberty Mutual. Those are references and image sources. With that, I would like to thank you for your attention, and I'll be happy to answer any question that you have.
Thank you so much, Professor Lee. Really appreciate it for a wonderful presentation. I think we learned a lot from your presentation. So I open the floor for any question from the audience. I have some question myself, but first we go to the audience to see if there are any questions. Thank you.
Yeah, by the way, I'm sorry, I don't know if you heard about the noise. So it is an unexpected construction noise. So hopefully you didn't hear much, but it was a little bit. I would like to apologize for that.
Sure. Okay. Thank you so much. Any question from the audience? One of the people is Yibo Kiang is asking how is the market for the product now, for the software that you have developed?
Yeah, so the one that I developed from Kinetica Labs. So Kinetica Labs was acquired by Velocity HS. Now all the product has been distributed through the Velocity HS. So it's still the tools are available through Velocity HS.
Thank you so much. Let me see if there is any other question. So, Professor Lee, I have one question myself. What suggestion do you have? Yes, we will go into Q&A. Alexandra, thank you so much. How do you? I think your presentation is a great example of how research to practice can happen. How we can conduct research at university and do not leave it there. So we transfer it into the practice and try to save lives or reduce the number of injuries. What rule of thumbs do you have for other researchers who are attending this call to transfer their research products into the practice and to the market and commercializing? Thank you.
That's a great question, and that is one of my biggest findings during my research career. So, as like a typical engineering professor, I was focusing on publishing and grant, and those what I have been focusing on. Then there is a kind of the unexpected event when the industry professional came to my presentation and talked about the potential of this technology. So I was very curious to learn more about if there is any way that this can be applied to the practice. And then that's when I conducted more than 100 interviews to really understand the potential of this technology. So going through all the process, what I found is that something that we are looking as a problem statement in the lab is much, much different from what industry is suffering. Particularly to translate research to the practice, I think the most important thing is not the cool technology. It's more about the need from the industry, the pain that industry has. For example, I think one good question that we can ask is, I'm sorry to talk about the money. Are you willing to invest money to buy this technology? That may be very simple question, but it is a money question. But that actually in behind the scene, what this question is asking, are you really suffering from this issue? Are you really putting your resources to have it? So that is my eye-opening moment for me to really understand the difference between typical problem that I see in the literature and the problem in the industry. And that's where I started digging into more and more to address those issues. So I know it has been long. So to make a long story short, so basically we are engineering research. We would like to try to apply to the real world, meaning that we really need to understand where and what the industry suffers. And then we need to understand it and to see that how our technology can address it. So that is something that I really appreciate as a biggest lesson from my experience.
Thank you so much. A wonderful response. So we should pay attention to pain points of the industry. Thank you so much. I'm going to the question from Q&A. Raul Valdez is asking, how do you estimate 17% annual MSD?
Yeah, that's now it has been distributed to the Velocity HS. So I have the Velocity HS, the investigate. So more than 500 organizations worldwide has been using it. And then the musculoskeletal injury cases. And then when they apply our technology, year over year, we measure the number of the injuries, right? So that it has been almost like 10 years. So now we have the cumulative report that shows that on average, year over year, we see the 17% of MSD reduction once they apply the vision-based technology.
Thank you so much. Victoria Kotan is asking, can we use this approach for dentist posture or other aesthetic postures? If we have captured picture of the dentist, she said that she knows posture estimation through Kinovid. It's another software that also can do that.
Right. They have a different context and different constraint, but we used to work with surgeons because in the surgical room, the postures of the surgeon is very tricky. So we would like to improve it and measure the risk. And also dentist as well. Yeah, so the way that it has been addressed, so it can be definitely applied to the dentist and the surgeons. Of course, each one give a very specific challenge. Now, in the workplaces, we cannot have a full line of sight, but at least we have a little bit room to move around. to have a better line of sight or avoid some of the occlusions. But in case of a dentist and the surgical room, it may not be possible because we are very in a confined room with also 2 or 3 people, assistant, and in a very small room and with a lot of the equipment. So it may be very challenging, but I still believe that this is something that we can addressing, and then camera can be much more closer, which is actually advantage. And then the hand movement, hand gest, the hand is also very important for the dentist and any surgeons. So it can be more specialized application for hand. By the way, we also apply to the hand. So the hand pose can be also very accurately estimated. So that is something also we can do. So yes, it is possible. And it just depends on the different context, but it is very possible nowadays. Of course, you need a lot, some of the a significant engineering effort to make it happen.
Thank you so much. Another question from Victoria: what can be done for workers carrying load on head or shoulder? We do have video data using AI.
So can you repeat what the overhead work?
Sure. What can be done for workers carrying load on head or shoulder? And do we have the video to be analyzed with AI?
Yeah, that's a typical way, right? If you are talking about the occlusion from carrying big things over your shoulder, there is a way that we can move around and then we can at least avoid the occlusions. But also nowadays the AI model can address at least short period of time of the occlusion, because we are talking about the video. So we are not talking about frames or images. So you have the previous frames of history, and then you have occlusion, for example, 1 second of 30 frames of the occlusion. And then if you see the next posture, actually AI can very accurately estimate what could happen in between those 2 frames. So if we are talking about the occlusion, my answer is yes, there are several techniques to address this short-term occlusion, so it's possible. And then if you are talking about intervention, really intervention, yes, now we have what this posture create the problems in your body. Now that is the professionals can think about what we can do. Also, if we train potential solutions with the AI provide potential answers. I hope this can answer the question, but if not, please let me know. I'll be happy to answer, respond.
Sure. Thank you so much. Victoria can type again. Thank you so much. We have another question from Denis Chavez. What about data management? How can we ensure that this type of data and technology isn't used by insurance companies to reduce coverage?
Yes, this is more like how the organization's data policy. This becomes very important issue, right? So it is. Let me think about it in this way. Insurance company. So this is again depending on the different policy. If you would like to strictly protect your workers and your privacy, maybe that is something that you can keep in your organization. But also another way to think about is that when I actually work on safety-related technology, I truly believe the insurance company is one of the big players and in our ecosystem. They can do actually a lot of things for us. Us means the organization and the companies. So rather than isolating all the different organizations and worrying about the data, actually without each individualized data, collective data can be shared to be used in a more in a creative way to reduce injuries. For example, insurance companies can provide workers' compensation discount when you apply these new emerging technologies, which is proven in the market, also that the organization also can recoup the investment they made from the discount of the insurance premiums. So there are several creative ways to work together, because all our objective is basically to reduce the injuries and illness in the job site.
Thank you so much. Thank you, Dr. Lee. The next question is from an anonymous attendee. And unfortunately, I have a little bit difficulty understanding the question myself. So I'm going to read the question. Any prototype usage that you provided using AI for ergonomic video-based assessment, like till what % it is benefit? So this is the exact question I'm reading, but I don't know.
What is the last one? What is the last question, the last sentence?
Yes, what % it is benefit, or what %
benefit?
Or how much percentage benefit does it provide? I don't know, perhaps maybe that's the question.
Yeah, I think then maybe the 17% MST reduction. But this reduction, I would like to make sure that, meaning that you have correct ergonomics program. So meaning that you have a program to monitor and use that information for your intervention. And if you have that process in your organization, we can achieve 17% MST reduction. That is the one, this is in our case. Okay? But the impact could be much different depending on the different context and how you are going to use this technology. 17% should not be regarded as just one universal number. It could be much higher than 17%, but it could be lower than 17% depending on how you use technology. Because in the end, it is depending on us, the people who use the technology, not the technology themselves.
Yes. Thank you so much. One of our attendees has raised his hand, Stanley Noddy. Stanley, if you want to state your question. Thank you. So I'm not sure if the mic works, but also, Stanley, if you want, you can type the question. So until Stanley can figure it out, I'm going to the next question from John Rosecrans. Do you have any actual fall incident data that you can compare to your fall risk data?
That is difficult question, right? So no, we don't have fall data. Fall is a significant issue, but that doesn't mean that fall happens while we apply to the construction site as well as in the building, but which is actually a good thing. So we haven't had any accident. But the very minor fall are like slip, trip. Yeah, that happens. And then that's the data that we collected from the construction site. But the old hazard does not necessarily connected to the falls. But if we would like to prevent falls, basically we need to eliminate fall hazard, and that's what we have been focusing on. And what we are trying to do is this fall risk detection, because already commercially nowadays people have been focusing on is a detect fall actually, and then connect to 911. That's the typical commercial product in the market. So our approach is very different. We would like to measure, detect fall hazard and risk so that people can be prevented. So that's what we are trying to now translate this research into the practice. And then if we the scale up this application, hopefully we can have some more data so that we can take a look at more about it. But in our case study, we didn't really have a lot of the fall and serious falls in our data collection, and that is not actually our proposal as well.
Thank you so much. So we are almost at the time. There are a couple of more questions. I'm going to read them very quickly. There is another question from Bernadette. If companies will buy the technology, does the company needs to affiliate with the developer of the AI or hire additional personnel with AI level education or training?
The current product that we commercialize, no. It is all you can just use it, and then you will have a consultation from the company. But if you would like to develop your own, of course, you need your own person. But the way that I say is that it's much democratized now, right now. So AI software and hardware is readily available. So if you would like to develop your own solution for the company, it's possible. But if not, if you just a product, you don't need anyone who develop this one. But of course, always in your organization nowadays, someone who understands AI definitely be helpful for its adoption.
Thank you so much. The next question, Sharia Bandekar. The question is that hope that you share the benefit and errors that you come across while researching on what about the funding.
Sorry, this one is what?
Sure. The question is hope that you share the benefits and the error that you come across while researching, and what about funding? It's a two-section question.
Sorry, what do you mean by funding?
I have no idea. Sharia, I think he's on the call.
Sorry for not clearly understanding.
Sure. Me too. I have no idea. But I think you talked about the benefits and the errors and how we can be successful focusing on pain points. I think that was one of the issues. And the last question is from Hoda from University of Leeds about ethical issues. So while we are tracking using these wearable sensors, is there any concern about ethical issues tracking data from workers?
Right, that is a very important issue. So in case of the vision-based MSD risk evaluation, of course, we remove the blur the people's face, and we don't disclose any identifiable information. And wearable data as well. You don't have to share it with your management. The way that we do right now is it's more about the individual coaching. We let each person know where you get exposed to the fall hazard, what kind of the things that you can do as a coaching. And then for the management in the construction side, we only share the hazard map. So we don't share with each identifiable information. So I think this is actually implies a bigger question, the ethical issue, privacy issue. It is, if we apply these types of sensors, of course, we have a very richer information, but there will be the line that we cannot cross. That is something I think we have to think about any creative way to address it, and how this can be much framed, these pros and cons of this technology, so that everybody understands the benefit and drawbacks, and then they see how this can be applied. So that is going to be very important. If I have a chance next time, I'm going to share what I have been doing with that issue, because that is very important and the big issue.
Thank you so much. I know we are almost at the time 11. Just maybe one or two more small questions, and if you can answer briefly, we really appreciate it. Thank you so much. A question from Dr. Alam. Can we use this kind of research, AI tools, to design PPE-like shoes for construction workers?
PPE shoes?
Yes, to design different shoes or PPEs for construction workers.
I haven't thought about it. The way that I approach this one is I'm actually thinking this kind of wearable-based technology as another PPE, something that is integrated into the PPE. So, for example, we have the vest and hardware. That is where we can put the sensors so that it can be used as our PPE, but at the same time collect the data to protect the workers. So I think all our PPE going to be very smart with the integration with the AI. So that is the way I look at that as a change of PPE means that PPE becomes much more smarter, not just protecting workers, but also the potentially eliminating our risk.
Thank you so much. Stanley, that raised his hand, he couldn't talk, open the mic. They asked, did you factor in the height of the worker because it affects the lift height and also the posture of the worker?
Yes, absolutely. So we use the typical using the anthropometric data, but in the real world applications in the company, in the product, people are able to put their own height and weight if wish. Otherwise, we are just going to use the way that what we can do is just the mesh. We also extract the mesh, people's body mesh, and then we have using anthropometry data and approximate a height, but this can be done also manually.
Thank you so much. And the last question, we are over the time, from Ali Zabihi Kulai. He's asking that can we use BEAM or GIS-based hazard information, such as predefined dangerous zone, into fund risk assessment system to improve accuracy?
Absolutely. That is what it can be done with the BEAM, GIS, and we actually try to do it. And the thing, it becomes basically digital twin and human-centric and digital twin that it can be seen as over time, not just the static BEAM, GIS, static digital twin. It is human-centric digital twin, which can show the changes over time. And then again, what if analysis through the digital twin. Sorry, let me just answer the question that we couldn't understand, but because that I just want to make sure to address all the questions. The question talked about the funding. So my guess is the question is talking about the funding for this technology. My experience in each organization has a certain part of the money can be used to improve the workers' safety and health as a discretionary fund. So we designed our product to be in the range of the discretion about typical organization. Hopefully that was the question. If not, if you shoot me email, I'll answer the question. Sorry about that.
Thank you so much, Professor Lee. In the comments, there were so many thank you notes and lots of congratulations and so much praise, and people really enjoyed the presentation. Thank you so much for your time. We really appreciate it. Thank you so much for people who attended. Wonderful. Please follow Dr. Lee's research, and some of them also asked to contact you after this presentation. Thank you so much for IEA for hosting this presentation. Thank you so much, Alexandra, for providing administrative support. Thank you, Haley, one of our PhD students who is helping with these webinars and is a very active researcher in exoskeleton research. I wish you a wonderful holiday season, and see you next time.
Thank you so much, everybody.